do a factoring of quadratics or something similar. Now go forth and factor. This video gives some additional examples of factoring. Please pause the video and decide which of these first 5 expressions factor and which one does not. The first expression can be factored by pulling out a common factor of x from each term. So that becomes x times x plus 1. The second example can be factored as a difference of 2 squares, since x squared minus 25 is something squared minus something else squared. And we know that anytime we have something like a squared minus b squared, that's a plus b times a minus b. So we can factor this as x plus 5 times x minus 5. The third one is a sum of 2 squares. There's no way to factor a sum of 2 squares over real numbers. So this is the one that does not factor. Just for completeness, let's look at the next two. This next one does factor by grouping. When we factor by grouping, we pull the biggest common factor out of the first 2 terms. That would be an x squared. That becomes x squared times x plus 2. And then we factor as much as we can out of the next 2 terms. That would be a 3 times x plus 2. Notice that the x plus 2 factor now occurs in both of the resulting terms, so we can pull that x plus 2 out and get x plus 2 times x squared plus 3. We can't factor any further because x squared plus 3 doesn't factor. Finally, we have a quadratic. This also factors, and I like to factor these also using a factoring by grouping trick. So first, what I do is I multiply the coefficient of x squared and the constant term. 5 times 8 is 40. I'll write that on the top of my x. Now I take the coefficient of the x term, that's negative 14, and I write that on the bottom part of the x. Now I'm looking for 2 numbers that multiply to 40 and add to negative 14. Sometimes I can just guess numbers like this, but if not, I start writing out factors of 40. So factors of 40, I could do 1 times 40. Well, now I just noticed I'm trying to add to a negative number. So if I use 2 positive factors, there's no way there's going to add to a negative number. It's better for me to use negative numbers that factor 40. A negative times a negative still multiplies to 40, but they have a chance of adding to a negative number. So, but negative 1 and negative 40, of course, don't work. They don't add to negative 14. They add to negative 41. So let me try some other factors. The next biggest number that divides 40 besides 1 is 2. So I'll try negative 2 and negative 20. Those add to negative 22. That doesn't work. Next one that divides 40 would be 4. So I'll try negative 4 and negative 10. Aha, we have a winner. So negative 4 plus negative 10 is negative 14. Negative 4 times negative 10 is positive 40. We've got it. All right, so the next step is to use factoring by grouping. We're going to first split up this negative 14x as negative 4x minus 10x and carry down the 8 and the 5x squared. Notice that this works because I picked negative 4 and negative 10 to add up to negative 14. So negative 4x minus 10x will add up to negative 14x. So I've got the same expression, just expanded out a little bit. Now I have 4 terms. I can do factoring by grouping. So I can group the first 2 terms and factor out the biggest thing I can. That would be an x times 5x minus 4. And now I'll factor the biggest thing I can out of these 2 numbers, including the negative. So that becomes, let's see, I can factor out a negative 2, and that becomes 5x minus 4, since negative 2 times minus 4 is 8. All right, I've got the same 5x plus 4 in both my terms, so factoring by grouping is going swimmingly. I can factor out the 5x minus 4 from both those terms, and I get the x minus 2. And I factored this quadratic. If I want to, of course, I can always check my work by distributing out, by multiplying out. So a check here would be multiplying 5x times x is 5x squared. 5x times minus 2 is minus 10x. Minus 4 times x is minus 4x. And minus 4 times minus 2 is plus 8. So let's see, this does check out to exactly what it should be. So that was the method of factoring a quadratic. And all of these factor except for the sum of squares. So we saw that factoring by grouping is handy for factoring this expression here. It was also handy for factoring the quadratic indirectly after splitting up the middle term into two terms. So how can you tell when an expression is appropriate to factor by grouping? There's an easy way to tell that it might be a candidate, and that's that it has 4 terms. So if you see 4 terms, or in the case of the quadratic, you can split it up into 4 terms, then that's a good candidate for factoring by grouping, because you can group the first 2 terms, group the second 2 terms. Factoring by grouping won't always work on expressions with 4 terms, but that's like the first thing to look for. So let's just review what are the same main techniques of factoring. We saw these on the previous page. We saw there was pull out common factors. There's difference of squares. There's factoring by grouping. There's factoring quadratics. And one more that I didn't mention is factoring sums and differences of cubes. That uses the formulas a cubed minus b cubed is a minus b times a squared plus ab plus b squared, and a cubed plus b cubed is a plus b times a squared minus ab plus b squared. One important tip when factoring, I always recommend doing this first. Pull out the common factors first. That'll simplify things and making the rest of factoring easier. One more tip is that you might need to do several of these factoring techniques in one problem. For example, you might have to first pull out a common factor, then factor a difference of squares, and then you might notice that one of your factors is itself a difference of squares, and you have to apply a difference of squares again. So don't stop when you factor a little bit. Keep factoring as far as you can go. Here are some extra examples of factoring quadratics for you to practice. Please pause the video and give these a try. For the first one, let's multiply 2 times negative 14. That gives us negative 28, and then we'll bring the 3 down in the bottom of the x. Now we're looking for 2 numbers that multiply to negative 28 and add to 3. Well, to multiply 2 numbers to get a negative 28, we'll need one of them to be negative and one of them to be positive. So, let's see, 1, negative 1, 28, or 1, negative 28, those don't work. Let's see, negative 2, 14, or 2, negative 14, those don't work. Hey, I just noticed the positive number had better be bigger than the negative number so that they add to a positive number. Let's see what comes next. How about negative 4 times 7, 4 times negative 7? I think negative 4 times 7 will work. So I'll write those here, negative 4, 7. I'll copy down the 2z squared, and I'll split up the 3z into negative 4z plus 7z, and then minus 14. Now factoring by grouping, pull out a 2z, that becomes z minus 2. Pull out a 7, and that becomes z minus 2 again, looking good. I've got 2z plus 7 times z minus 2 as my factored expression. My second expression, I could work it the same way, drawing my x and factoring by grouping, that kind of thing. But it's actually going to be easier if I notice first that I can pull out a common factor from all of my terms. That'll make things a lot simpler to deal with. So notice that a 5 divides each of these terms. And in fact, I'm going to go ahead and pull out the negative 5 because I don't like having negatives in front of my squared term. So I'm going to pull out a common factor of negative 5. Again, it would work if I forgot to do this, but it would be a lot more complicated. So negative 5v squared, this becomes plus 9v. since 9 times negative 5 is negative 45, and this becomes minus 10 since negative 10 times negative 5 is positive 50. Now I can start my x and my factoring by grouping, or I can use kind of a shortcut method, which you may have seen before. So I can just put v's here, and then I know that whatever numbers go here, they're going to have to multiply to the negative 10, and they're going to have to add to the 9. So that would be plus 10 and a minus 1 will do the trick. Those are all my factoring examples for today. I hope you enjoy your snow morning and have a chance to spend some time working in ALEX. Bye. This video is about working with rational expressions. A rational expression is a fraction, usually with variables in it. Something like x plus 2 over x squared minus 3 is a rational expression. In this video, we'll practice adding, subtracting, multiplying, and dividing rational expressions, and simplifying them to lowest terms. We'll start with simplifying to lowest terms. Recall that if you have a fraction with just numbers in it, something like 21 over 45, we can reduce it to lowest terms by factoring the numerator and factoring the denominator, and then canceling common factors. So in this example, the 3's cancel, and our fraction reduces to 7 over 15. If we want to reduce a rational expression with variables in it to lowest terms, we proceed the same way. First, we'll factor the numerator, that's 3 times x plus 2, and then factor the denominator. In this case, it factors to x plus 2 times x plus 2. We could also write that as x plus 2 squared. Now we cancel the common factors, and we're left with 3 over x plus 2. Definitely a simpler way of writing that rational expression. Next, let's practice multiplying and dividing. Recall that if we multiply two fractions with just numbers in them, we simply multiply the numerators and multiply the denominators. So in this case, we would get 4 times 2 over 3 times 5, or 8/15. If we want to divide two fractions, like in the second example, then we can rewrite it as multiplying by the reciprocal of the fraction on the denominator. So here we get 4/5 times 3/2, and that gives us 12/10, but actually we could reduce that fraction to 6/5. We use the same rules when we compute the product or quotient of two rational expressions with variables in them. Here we're trying to divide two rational expressions, so instead we can multiply by the reciprocal. I call this flipping and multiplying. And now we just multiply the numerators and multiply the denominators. It might be tempting at this point to multiply out, to distribute out the numerator and the denominator, but actually it's better to leave it in this factored form and factor it even more completely. That way we'll be able to reduce the rational expression to cancel the common factors. So let's factor it even more. The x squared plus x factors as x times x plus 1, and x squared minus 16, that's a difference of two squares. That's x plus 4 times x minus 4. The denominator is already fully factored, so we'll just copy it over, and now we can cancel common factors here, and we're left with x times x minus 4. This is our final answer. Adding and subtracting fractions is a little more complicated because we first have to find a common denominator. A common denominator is an expression that both denominators divide into. It's usually best in the long run to use the least common denominator, which is the smallest expression that both denominators divide into. In this example, if we just want a common denominator, we could use 6 times 15, which is 90, because both 6 and 15 divide evenly into 90. But if we want the least common denominator, the best way to do that is to factor the two denominators. So 6 is 2 times 3, 15 is 3 times 5, and then put together only the factors we need for